Rock, paper, scissors seems simple, but there's actually some strategy behind it. Rock, paper, scissors is supposed to be a game of random chance, right? I mean, the Nash equilibrium, or the optimal strategy, is to just play completely randomly. But what if we tried to teach a computer to play it, not randomly, but intelligently? Humans aren't that random, and subconsciously we form patterns like rock, paper, rock, or scissors, scissors, paper. And we can use that to give our AI a statistical edge. In this video, I'll show you how I built an AI in Roblox that predicts your next move. I built this simple system in Roblox Studio where you basically just press the buttons to play and it records your wins and losses. Right now, the AI is just playing randomly, so let's implement our first model. This is the frequency model, which just counters your most frequent move. It basically just gets your history of moves and counts the most frequent one and counters it. Alright, this sucks, so let's move on to something better. This is a first-order Markov model. Here's how it works. Instead of just counting how often you play rock or paper overall, it looks at what you tend to play next after each move. For example, if you usually follow rock with paper, the AI will remember that pattern and use it to predict what's coming next. We basically make this matrix, and we count how many times that certain pattern appears and choose that option if our last move lines up. It's a step up from frequency, and it actually starts catching on to short-term patterns in your playstyle. But we can make it better by using a second-order Markov model. Instead of just looking at your last move, it looks at your last two moves and uses that to predict what's next. For example, if you often go rock then scissors then paper, then every time the AI sees rock followed by scissors, it's going to expect paper next and counter it. Let me show you how it works with a simple dataset. Say your move history looks like this. The AI slides through that history, looking at every two move sequence and what came next. And here's what the AI builds from that. So now, let's say your last two moves were rock and paper. The AI sees that rock paper has led to scissors twice before, so it predicts scissors again. And since it wants to beat that prediction, it plays rock, the counter to scissors. That's it. It's reading your patterns and learning how to counter them. Okay, now let's crank the complexity up a bit. This is the N-gram model, or what I call the pattern tree model. Think of it like this. Instead of just looking at the last one or two moves like Markov models, it builds a tree of move sequences. You give it an N, how far back it should look, and it learns every path of moves that length plus what move usually follows. Let's set N equals 3. First, the AI slides through your history, looks at every 3 moves sequence called an N-gram, and records what came next. It finds that rock, paper, scissors appears twice, and both times the next move is rock. The AI looks up that exact pattern and finds that rock is most likely to come next. The N-gram model is essentially a scaled-up or generalized version of the Markov model. Alright, now it's time to get a bit more advanced. We're moving into the world of reinforcement learning, specifically Q-learning. Q-learning is a way for an AI to learn from experience by trying moves, getting rewards, and remembering which moves worked best in specific situations. Think of it like this. If the opponent played rock last turn and scissors before that, what move usually wins next? Imagine the opponent just played scissors, then rock. The AI creates a state, scissors rock. It looks in its Q table, a memory that says, when I've seen this situation before, how well did each move do? Let's say it sees this. Since scissors has the highest score, the AI will likely pick scissors, unless it's still exploring new moves by choosing randomly. After it plays, it checks, did I win, which adds 1 point. Did I tie, which subtracts half a point. Did I lose? Which subtracts 1 point. But hey, we don't just add 1 or -1 to the score. We actually update the score like this. But wait, that's just the reward, meaning that the AI may be too trusting of this action. We wanted to learn more gradually, so let's add a factor. But hey, that future reward variable is kinda weird. The future reward is based on the state after the outcome, so if we win, then the next state is rock paper because the player lost. But hey, the next reward is only 2, so we downgraded. Well, this formula does work if the player shows patterns. For example, if the player played rock, scissors, etc. Let's say the current state is rock, scissors, so the player will play rock and our AI plays paper. The AI won and gained a point. Let's record our score in our Q table. Then the next state becomes scissors, rock. Our AI randomly played rock and gained 1 point. But since the future state is rock, scissors and the reward is 0.1, then we add 0.1 to the formula as the future reward. Let's record our score in our Q table. We see that as we repeat the states, the AI learns this pattern. This is a simplified version of the Q-learning update formula, which helps the AI gradually adjust its expectations based on rewards now and in the future. And little by little, it gets smarter. Now the last question is basically, what model do we use? I mean, some models are better in certain situations. For example, Q-learning kinda sucks at the beginning and 3-gram tree kinda sucks if the player is more oriented to one-move patterns. That's where the meta AI comes in. So I built something I call a meta AI. Basically, an AI that chooses which AI model plays against you. Every time you play, the meta AI secretly runs all 5 models: frequency, Markov 1, Markov 2, pattern tree, and Q-learning, and checks which one would have predicted your move best. It gives each one a score, +1 if it would have beaten you, -1 if it would have lost, 0 for a tie. Then it updates each model's score over time, but with a twist, it uses decay. That means it gradually forgets older results and gives more weight to what's working right now. So, if you suddenly start playing differently, the meta AI starts trusting the models that are catching on and drops the ones that are falling behind. When it's time to make a real move, it adds the scores of every model. If a score is less than or equal to 0, then it uses 0.01. Then the meta AI chooses a random number between 0 and the sum. What we basically do is then choose randomly between each model as shown. A model with a higher score has a higher chance of being chosen. It's kind of like a team of AI players, and the meta AI is the coach that decides who gets to play based on performance. Well, that's how the AI works. Anyway, here is some gameplay. I'll give the game description below, and it's also uncopylocked and open source for anyone to use.